Part 1. The Vision. My goal in this project is to build an alpha-type Stirling engine and analyse its operation. Part 2. The History. The Stirling engine was invented by Robert Stirling in 1816. The name might be a giveaway. Initially, they were used as an alternative to steam engines in factory work, capable of lifting up incredible masses. However, they could only do this at a very slow rate. One of the early examples was capable of lifting hundreds of tonnes. However, it only output 23 newtons, so the work took a long time to be done. Stirling engines were seen as a good alternative to steam engines when they were first developed, as steam engines had frequent mechanical problems like boilers exploding and seals breaking. However, throughout the years, steam engines became more efficient and, due to their faster power output than Stirling engines, gradually displaced them in the use of factory work. Stirling engines began to see use as cryocoolers in the early to mid-1900s. These worked by imparting a mechanical force on the Stirling engine, causing the pistons to run, increasing the temperature difference between them, much the opposite of a traditional Stirling engine. This is similar to how running a current through a solenoid can create a magnetic field, and running a magnetic field through a solenoid will induce a current. These cryocoolers were very efficient, reaching negative 200 degrees Celsius, and some of the more efficient ones even pushing minus 250 degrees Celsius. This had a number of uses, especially in the early 1900s, as getting very cold refrigeration was hard. However, these cryocoolers powered by Stirling engines saw little commercial use as they required large amounts of power and were much too large to put in a household refrigerator. Stirling engines then saw a subsequent drop in usage as cryocoolers became superseded by other methods of cooling, both in commercial and in very low temperatures for scientific use. They saw very little use until 1996, when the Swedish Navy installed a number of Stirling engines on their submarines. Stirling engines had a large number of uses in submarines, as they were much better at keeping submarines stealthy than nuclear or diesel powered, which are the main two types. The reason being, both nuclear and diesel engines made a lot of noise and also produced fumes and pollution, which was easily tracked by other navies. This meant that the Stirling engine submarines could be more indetectable, which is obviously a bonus in the submarine industry. There are three types of Stirling engine: alpha, beta and gamma. Each of these operate by compression and expansion of hot and cold gases, however they do so in slightly different mechanisms. The alpha type Stirling engine has got two separate pistons, totally separate, and they just act on each other through a tube between the two of them. The beta Stirling engine has two pistons, however one does not seal all the way to the edges, which allows hot air from the bottom, where it's heated, to pass up and into the middle chamber, which is where the cold air is, which is then compressed and expanded by both the pistons. Gamma type is similar to the beta type, however it tends to be more efficient as it separates the hot and the cold. Also, there is a displacer in the hot chamber of the gamma type, which is usually much larger than the cold, but drawn here at the same size to make it a little bit clearer. This displacement acts to help funnel the hot air into the cold chamber to increase the amount of compression and expansion this engine can have, increasing its efficiency. In general, the alpha and the gamma engines tend to be more efficient than the beta type engine because of the close proximity of the hot and cold chambers in the beta engine. I've decided to build an alpha engine as it's more efficient than a beta, and it's much simpler to build than a gamma engine, as getting the displacement in there is quite difficult. Some of you might be asking, what uses are there for Stirling engines? As they seem to be inefficient compared to most modern types of engines, expensive, slow with their energy, a whole host of other problems. However, there are quite a few uses of them. As mentioned earlier, they've been used as cryocoolers when energy and work is applied to them. Been used in submarines, as they're far quieter than most other types of engines. But what I haven't mentioned yet is they're used in a number of power generation methods, such as solar, geothermal and nuclear. All of these types, as a general rule, utilise Stirling engines to take heat, whether it's from the sun, from hot rocks below the earth, or from a nuclear plant, takes the heat and converts it into mechanical work, much like they're intended to do. The usage of Stirling engines in these power generation methods is quite efficient, as it produces no pollution. For my design, I've decided to build an Alpha type Stirling engine. Bing! This is my engine. As you can see, it's pretty much the stock design. 2 pistons with glass syringes, 2 pieces attached to a flywheel, each with nuts around the rim for inertia, little arms, and little pieces of armature to hold the ends of the syringes. The ends of the syringes are attached to the armature with zip ties. They're red, so they're quite hard to make out. However, they're there to make sure the syringe can't slip out the bottom. One alteration I did have to make was the flywheel. The pieces of rod we were given were too thick to fit in the flywheel. So I had to MacGyver up basically an orbital sander using a drill and a piece of file to get it down to the correct size, fit through the bearings. Speaking of bearings, there's 2 bearings in here, one on each side. They basically ensure that the flywheel spins smoothly and reduce friction, which will increase the efficiency of the engine overall. This support here had a couple of problems, as you can see by the purple line around it. This was due to basically it snapping when I was trying to put the bearings in. However, this was easily rectified with the use of super glue, as well as using a 3D pen to act much like a welding device, attaching the plastic. Now it is very strong and it's very capable of supporting the Stirling engine. The other end was also a piece printed off. However, this piece was quite difficult to print and I had a number of misprints. My first misprint turned out like this, which was clearly not the intended result. My second print ended with this, which is also clearly not the intended result. The first of those was due to not putting enough glue on the base of the 3D printer, while the second one was caused by a jam with the PLA filament. The tube here at the end was a more difficult way, as it had to be completely sealed around the syringes to reduce air loss, which would decrease the efficiency of the engine as a whole. How this was dealt with was with a piece of 9mm tube and a heat gun, slowly and gradually stretching out the tube until it went over the ends of the syringes, creating an airtight seal. And during construction, this was one of the biggest difficulties. It took me probably 4 or 5 different tries to be able to stretch the tube out without having it pop and burst and inevitably have holes in the seal. One final thing you may have noticed with the engine is the nuts on the edges of the armature here. This is because I had a little bit of rod sticking out the end, as I was not able to get this to the perfect length, as well as the nails which I used as supports being very long. So the 2 nuts here were just used to hold the armature in place as it spun around. Part 4. The results. Before we analyse my Stirling engine, we must familiarise ourselves with how a Stirling engine works. This here is a diagram of the Stirling cycle, where you can see processes 1, 2, 3 and 4 in that order. Process 1 and 3 are both isothermal, and process 2 and 4 is where heat is added or removed. In this case, process 2 has heat removed, pressure and volume both equalise, and then process 4, heat is added before work is done and the process repeats again. In the Alpha style Stirling engine, because of a 90-degree offset, there's kind of a slight kick on, where during this phase, the 90-degree offset helps kick this forward while this kicks. As we can see, the Stirling engine didn't quite get on a self-perpetuating cycle. However, there was a significant amount of kickback from the cylinders, meaning it wouldn't have been too far off. Despite this, we can then say our theorised efficiency based on the temperature of the room and the temperature at which the candle burns at, 72%, is clearly off the mark, with efficiency being reduced by factors such as friction, non-uniform heating by the candle, as well as potential air leaks in either the hose or the syringes. Furthermore, the flywheel is slightly offset from the syringes, which would also likely increase friction and thus reduce the efficiency. Despite this, you can still draw parallels from the cycle, and this is solely based on the amount of kickback from the engine we did get. As the Stirling engine did not perpetuate its motion we cannot get an accurate analysis for the amount of work done or the potential work done by this engine. As a result, it's increasingly difficult to calculate the true efficiency of the engine, as we weren't able to get power readings which were necessary for it. Ultimately, if I was to build this Stirling engine again, I would make some modifications to the design. I'd use larger syringes, which would allow a greater amount of potential energy stored as heat in each syringe. I would also use one centralised flywheel, as the two flywheels being slightly offset I believe was a cause of the friction. I'd also have a tighter fitting between the arm and the edge of the syringe, as I feel like that was rattling, which indicates a loss of energy as well. Despite this, I feel like the engine was a moderate success, as it did manage to kick back, showing that there was some semblance of the Stirling cycle, even though it did not perpetuate its motion.